So good morning to all. So this is Selumar from SNS College of Technology and Department of Computer Science Engineering. So now I am going to tell about the paging concept in memory management. So paging. So first of all, the paging is a physical address phase of a process, and it can be non-continuous. So the process is allocated physical memory whenever the latter is available. So we have a two kind of chunks. So it is avoid external fragmentation and avoids the problem of varying size memory chunks. So we divide physical memory into fixed size blocks are called frames, and the size is power of 2. So between 512 bytes and 16 megabytes. So divide logical memory into blocks of the same size, it is called pages. So keep track of all frames. To run a program of a size n pages, need to be find n free frames and also load frame. So set up as a page table to translate logical to physical address. So it is backing storing the likewise split into pages. So still it have as a internal fragmentation. So address generated by CP is divided into two concepts. One is a page number, one is offset. So page number is P is used to an index into a page table, so which contains a base address of each page in a physical memory. So page offset D is combined so with the base address to define the physical memory address that is sent to the memory unit. So page number is a m minus n and a page offset is n. So page number is defined as P and the page offset is defined as a D. So it is a paging hardware concept. So in this diagram we have a CPU and a physical memory. So in between CPU and physical memory we have a page table. So page table contains a logical address as well as physical address. So logical address is called as a D offset and physical address as a D offset. So whenever we going to send the page to physical address, the page number sent to the page table and the page table number is sent to the physical address. So we cannot send the page directly to the physical address. Page model of logical and physical memory. So in a logical memory we consider different type of pages 0 1 2 3, and different kind of physical memory we contains page table contains 1 4 3 7 is pages and the page numbers. So page numbers assigned 0 to 1, page number 1 to 4, to page number 2 is assigned to 3, page number 3 is assigned to 7. It is a page table. So different kind of pages 0 to 1 4. So we then the physical memory assigned to the page frame number is 1, the frame number 1 is contains page 0. So paging example. So in a paging example we have used n equal to 2 and m equal to 4 bytes. So the 32 byte memory and the 4 byte pages. So in a logical memory we contain the 0 to 15 frames. In a page table we only assign the 4 frames, first 4 frames. In a physical memory the frame is all directly allocated to the physical memory based on the page numbers. So calculating internal fragmentation. So we need to have a page size and the process size, and we need a page numbers for is calculating internal fragmentation. So process view and physical memory now very different, because it is implementation process can only access its own memory. It is a free frames. So in a new process, the new process contains pages 0 1 2 3. So it is a free frame list. In a new process, page table occurred in the physical memory, so we have to rearrange the page frames in a main memory. So this is the before allocation diagram. So this is the after allocation diagram. So before allocation diagram we have know the new page tables not occur in the physical memory, but after allocation we have to insert the pages in the frames, all frames. So implementation of page table. So page table is kept in a main memory. So we have two different page table based registers and page table length registers, two registers. So page table based register points to the page table, and page table length registers indicate size of the page table. So in the scheme, so every data or instruction access is required to memory access. So one for the page table and one for the data instruction. So the two memory access problems can be solved by the use of a special fast and a lookup hardware. So it is catch called associate memory or a translation localized buffer, like translation localized buffers. So some transaction location buffers store address space identifiers. So in each TLB entry, so uniquely the identify each process to provide address. So space production for that process. So otherwise you need to flush at every context switch. So the TLB is typically small. It contains a 64 to 1024 entries. So on a TLB mesh, the value is loaded into the TLB for faster access next time. So replacement policies must be considered. So some entries can be wired down for permanent past access. So associate memory. So associate memory, it is a parallel search. We have a page number and a frame number. So it is have an address translation of P comma D. So if a P is an associate register, get a frame hash out. So otherwise get frame from page table in a memory. So page hardware with a TLB. So So we use using a transaction look side buffer in a page table concept. So we have CPU and a physical memory. So in between physical memory and CPU, we have used a TLB and a page table. So first we have to send the logical address to page number. So the page number is stored in a TLB, and this pre number is also stored in a TLB. So when the page number is hit in a TLB, so the TLB hit is 1. So then the page table is directly moved to the TLB. So when the TLB is missed, it is directly moved to the TLB page table. The page table contains numbers. The numbers moves to the physical address. So after hit, the page TLB hit plus physical is added, then move to the physical address. So how to calculate the effective access time? So effective access time called EAT equal to 1 plus lambda A plus. So each and every effective time is access for every hit of the page hit or TLB hit. So memory production, so we have a valid and invalid bit attached to each and entry in the page table. So memory production implemented by associating a production bit with each frame to indicate if read only or read write access is allowed. So we have any violation result in the trap to the kernel. So we used valid indicates that then associate page. So in the process logical address space, and it is there's a legal page. So invalid indicates that the page is not in the process in logical address space, or use a page table length registers. So this is the valid or invalid bit. The page tables contain a frame number, and a valid or invalid means we have a n number of V options. It is an invalid bit, so that the 6 and 7 are valid bit. So I mention as I valid is mentioned bit. Shared pages. So in a shared codes and a private code and a data, so shared pages means we have similar to multiple threads and sharing the same process space, and also useful for inter-process communication if a sharing of read and write page is allowed. So in the private code and data means each process keeps a separate copy of a code and data. The pages for the private code and the data code. So this is shared example. Sorry, this is a shared example. So we have a process P1 and a process P3. So in a process P1 contains a page table for a P3 and a page table for a P3. The page table for a P2 is shared, and the entire physical memory is a data 1 and a 3 and EDT and ED2. So in a physical memory, all the pages are shared in and store the data. So this is my reference for this topic. Thank you.